very moist, and the water potential in the xylem is close to zero, even can go above zero. And in those periods then, there's more pressure in the xylem than there is in the atmosphere, and the bubble gets pushed out the same way it came in. So root pressures and stem pressures, pressure potential greater than zero in xylem, and this typically happens in the spring in a climate like ours, when we're going from frozen to unfrozen. You can get pressures in the xylem, in the stems of trees and things that are above atmospheric pressure. Just like you tap a maple tree, right, in the spring, in the late winter, early spring, you tap a maple tree and the stuff comes out. That's mostly from the phloem, but there are pressures above zero in the vascular system of those trees. And controversial other techniques that I refer you to this plant phys topic to read about further. So this one is actually pretty nice. Here's the book, the website, and this one written by people at Harvard University talks about cavitation and refilling those embolisms in the xylem once cavitation happens. So please have a look at this. There's a lot of references. A lot of them. All right. Some more pictures before getting to data graphs. What do we have here? These are the perforation plates between two vessel members in whatever species this is. In B, transverse section, this just shows pectins in the cell wall of these transporting cells. These are two woody plants that shows, and this one is oleander, this one is oak, type of oak. And you can see that sometimes these vessels that are formed in woody plants seem to have a lot to do with each other. You get a line of similarly shaped vessels in the cross-section of the wood in a plant like this, versus this one where they're kind of, each one is distinct. And you can read about some of that stuff here. Here's a vessel, here's a vessel, here's a vessel. Here's the perforation plate between these two vessels that just happen to be sliced through. So you can see how that is. And see, really, there's nothing there. It's like open. And this one shows a bordered pit, similar to this picture in the book, where here's the torus, here's the cell wall, and it looks like it forms a solid barrier across there, but it doesn't, and the water can easily go around it, around this torus in the middle. So just some pictures of xylem. Let's get to the good stuff. Here's a study that looked at embolisms in xylem. So, Mel Tyree. Okay, detection of xylem cavitation in corn under field conditions. Yeah, how do you know when one of these embolisms happens? You listen very carefully when you hear it go pop. That's how you do it. Ultrasonic acoustic emissions. That's what they call them. Ultrasonic acoustic emissions. What's that? It's a little pop. So they've got a transducer that measures these, and they put it on the stem of a plant, and they collect data and listen for these little clicks or pops.
Can you actually hear it?
Ultrasonic, so you'd be hard pressed with your ear to hear it. You need this transducer and then some amplifiers and stuff, and then I guess you could put a speaker on it and have it go pop, pop, or something. But no, not with your ear. But anyway, they're really common. So look at this. Here's day of the year. Forget the Julian word, that's incorrect. Here's the day of the year on x-axis, and here's the cumulative acoustic emissions per day, right? How many of these pops they find in a corn plant? 5,000, 10,000, 15,000 in one day. Here's the soils drying out, then they got rain, then they irrigated, and then these pops go way down again. So lower and lower water potentials, more and more, and then higher water potentials, you don't have them. They're very common. So here's the acoustic emissions per minute, and this is one day. For well-watered corn, you see here, and for the drought-stressed corn, you see, 15, 20 of them per minute in these corn stems. So each one of these is blocking off a little bit of the hydraulic system and reducing the hydraulic conductivity of the vascular system. For this data set, time of day here shows the xylem water potential, the pressure potential actually in the xylem. I don't know if they did the ozonic, but they call it pressure potential. Anyway, so for this droughted corn, you see you get down to -1 megapascal midday, or for the well-watered corn. For the droughted corn, you're down at -1 3/4 megapascal. And that's associated with a lot more of these acoustic emissions. A lot more embolisms. Here's another study also from Altair. Yikes. Okay, so here's water potential in the stem, and here are these relative cumulative acoustic emissions. So how many of these pops you get? Okay, so we're starting -1, 3, 5, 7, 9, 11. So drying out this way. And you see for 1, 2, 3, 4, these curves, which represent 4 different species, as the water potential becomes more negative, you get more and more of these embolisms. But different species vary. So A is Abies balsamea. You know that one? Balsam fir. Doesn't grow very easily in Nebraska because, not because of the cold, but because of the drought. You can't handle the drought. J is Juniperus virginiana. That grows all over the state. Noxious weed, you might say, in Nebraska. It's much more resistant to these disruptions of the vascular system than something like balsam fir. So that may have something to do with the distribution of these species across the North American continent. Here are some other species showing the same behavior. Okay, so again, same species, same water potential on x-axis, but now instead of the number of these acoustic emissions, percent loss of conductance in the xylem. So how do you measure that? You can measure it by, okay, so we take this water flow equation. If we have a water potential, we take a piece of a stem like this, and let's call it A and B. We take the difference in the water potential between these two coins. And measure a flow rate. We can solve this. Okay, so for example, you can take a piece of a stem, attach a rubber tube to each end, and supply a difference in pressure potentials across that tube. Either high pressure here, low pressure here, or vice versa, or however you do. You can establish difference in water potentials. You can measure the flow rate of stuff through that piece of stem here, and that way you can quantify the conductivity of the piece of stem that you're working on. So by doing that, they can measure the loss in conductance at different parts of the day, and show that, sure enough, as the water potential become lower and these embolisms increase, the tissue loses its ability to conduct water. Okay. Well, here you see some pictures. I don't know why this seems out of place. You see some more pictures of these border tabs. Okay? Now, 5 minutes. All right, 5 minutes. Sure.
Is the equation right?
Oh, yeah, you're right. You're right. Good one. Yeah. There you go. Okay. Yeah, that's right. Thanks. Okay. That's the same as this equation, by the way. Except now instead of conductivity, I have resistance, or conductance, I have resistance in this equation. All right. Even though conducting cells in the xylem are dead, their hydraulic properties aren't necessarily constant. So we've already seen this with development of embolism in these conducting cells. But there are other more subtle differences that have been observed. And this paper in Science discusses some of that. They looked at 19 angiosperms, 5 conifers, 3 ferns, and showed that their results were similar for all of these species. And that is, when they made these measurements of resistance in a piece of a stem of a plant, by putting a difference in pressure potentials across that piece of stem and measuring the flow rate through there, through the xylem of that piece of stem, they were able to calculate conductivity for this piece of stem. What they found was that if they used distilled water, they get a different conductivity than if they used water with some ions dissolved in it. And that doesn't make sense. If that doesn't make sense in terms of what we know about flow in the xylem from this iron plus we equation, right? Because convective flow, difference in pressure potential is driving that flow. Why should what's dissolved in that fluid influence that flow rate? It's the pressure that's doing it, not what's dissolved in the fluid. So this was confusing for them, and that's why they ended up writing this paper. So let's examine a little closer. Here's a picture from the paper itself. All right, so here is just a typical experiment at A, where the flow rate adjacent is here on y-axis, time here, and they connected their piece of stem with tubing and supplied pure water through there and measured a flow rate of about 0.4 milligrams per second. Then they started introducing solutes into that water stream through, dissolved whatever it was, potassium chloride in that water. And this is 0.5, I think, millimolar. 0.5, 1, 2, 5, 10, 20, 50 millimolar concentration of calcium chloride. Small concentrations. But look what happens to the flow rate. Increases. Then they switched back to pure water and it decreased again. How can that be if the xylem is dead and those cells are just tubes? They scratch their head. Okay, this shows similar information as this one, flow rates versus potassium chloride concentrations. And you can see that increasing concentration, increased flow rate through these pieces of stem. They did it in all kinds of plants and got the same results. All right, what's the, okay, well, I guess this one shows that the concentration, ionic concentration that they're looking at, these millimolar concentrations of potassium chloride, are typically found in plants, in the xylem cell of plants. Very small concentrations, they don't affect the osmotic potential very much. But somehow they affect the hydraulic conductivity of the system. They also did an experiment with living tissue. So here's a plant that they had growing, I think this is tobacco, yeah, this is tobacco. And what they did with these tobacco plants is they peeled off the outer part of the stem that contained xylem vessels in it. And so they had these living peels off the stem, and then they hooked up their tubes to the end of those and supplied them with water and measured flow rates and things through that living system. And also found the same thing, that when they used distilled water, low conductivity of the xylem. When they used artificial sap, high conductivity of the xylem. So, how do you explain these results? Scratch your head and talk to a lot of people and come up with an idea and get it published in Science. Not bad. Okay, so here's a key to what they're doing. They were able to refine, this shows a piece of a stem with the tubes on the end of it. And they were able to refine this so that they could look at a very small piece of stem that only had one vessel in it. Only one. Not a bunch of them next to each other, but only one vessel. What's more, they were lucky enough to find, well, okay, let's not get into details. When they measured the flow rate through one vessel, it didn't matter what the ionic concentration was through that. Same flow rate. It was only when the vessel diverged, or they had more than one vessel, that they were able to show this change in the flow rate through that piece of stem, the change in the hydraulic conductivity through the stem. Here's what they discovered, or what they hypothesized. Among the cell wall constituents, pectins are known for their gel-like properties and their shrinking and swelling behavior. Shrinking and swelling behavior. Okay, so here, remember this picture back here. All this pink stuff around the xylem vessel, these are pectins, this pinkish stuff here. So these pectic substances are found in all cell walls, and especially in cell walls of xylem. Pectins are known for their gel-like properties and their shrinking and swelling behavior. We suggest that shrinkage of the pectic matrix in response to ions increases the size of microchannels, increases the size of these pits between adjacent vessels or between the tracheas and the vessels, and changes the hydraulic conductivity of the system. So with pure water, these pectic substances lining the cellulose fibers in the xylem vessel, or in the pit between one vessel and another. With pure water, these pectic substances swell up, get bigger, and make this channel smaller. With some ionic solute in the water, these pectic substances shrink, increase the size of these connections between vessels, and decrease the resistance to the flow of water. So just because the xylem system is dead when it's mature and functional, the conducting elements anyway, doesn't mean that their properties are constant. We see increased resistance with formation of embolisms and changes in conductivity with respect to what's dissolved in the water that's moving through that xylem vessel. Now, typically, plants don't move distilled water through themselves. This is natural. But it just shows that this is, even though the cells are dead, it's still a dynamic system. All right? See you a week from today.